and some of them I actually was making just 10 minutes ago, so they might have typos in them. All right. And one thing to, as I said, uh, be sure to ask lots of questions and let me know how things are going. Um, right. So this is, of course, on the theory of computation. So uh, um, Hilbert in 1900 something. I don't know if that's when gave his talk or whether that was when he was born, somewhere in there. He had a list of questions and he asked about what computation is. And Gödel is a logician who proved really amazing things. And back then they didn't have computers yet. They just had math and logic. And so we're going to think about right now, we're going to think about computation from the perspective of logicians, since these are logic slides. All right. So we're going to have various variables, and the first variable will be p, and what it's going to represent is some computational problem, right? So let's just give it an example here. P might be the sorting problem, right? So everybody knows sorting. Uh, then I can be an input to the sorting problem, and the input I is the input to the computational problem, which for sorting is just an array of numbers. The In computer science, we're going to assume that the input is just some arbitrary binary string. And then what P of I is, right? P is a computational problem, and P of I tells you what the required output is, right? So for sorting, the required output is the same list of numbers, but in a sorted order, right? So this is just some notation so we can describe computation. And then we want to say, well, what does it mean for sorting or computational problem P to be computable? And it means some algorithm can compute it, right? So let A represent an algorithm. Sometimes often we'll use M for a machine. Why machine? Because Turing designs Turing machines, and so theory people often use M for machine, but it's the same thing. All right, so what might our algorithm be? Well, it might be insertion sort or selection sort or merge sort. And and in this course, if you just say a machine, it tends to be assumed it's a Turing machine, but you can have it be a Java program or whatever kind of machine algorithm you want. Um, all right, so then if A is an algorithm and I is an input, then what is A of I? Well, it's going to be whatever the algorithm outputs on that input. So if it's insertion sort is the algorithm, then it's whatever insertion sort returns. And what do we need? We need that if the algorithm is computing the problem, then we need that the output is as required. And so what are we going to write? We're going to just see here that the output of the algorithm on the input is the same as the required output for the problem. Everybody good with this notation, right? And then if we're doing logic, if you've taken 1090, then these variables are are objects, um, just like when we do for all x, these are objects. And this is just a Boolean statement, which is true if the algorithm gives the right answer for the computational problem on input I. Right? Any questions? Everybody good? All right. So we want to, I think in often in your career as a mathematician, in fact, often in computer science and in your life in general, it's useful to think about things logically. So you have some statement in English and you want to express it as in logic, and the reason for that is because then when you're trying to prove it, there's some tools for how to mechanically prove a statement in logic. So we might want to say computational problem P is computable, right? Anybody guess what does that mean to be P to be computable? Uh, I can actually see you. Usually when I do this, I get to see your pictures as well. I don't know why I'm not seeing your pictures as well. Maybe if I here we got a couple people up there. Maybe I'll be able to see you when I open the screen. And I don't know why it's not showing me. Often it did. All right, so we want to say P is computable. Well, what does computable mean, right? We need to define these terms. And it means uh, that there's an algorithm that computes it, right? To be computable means there's an algorithm to computable, right? To be paintable means that it can be painted, right? So if it's computable, it means it can be computed, right? And what computes it? Some algorithm, right? Now, which algorithm, right? Do we want to say there's some algorithm that computes it or every algorithm that computes it, right? Well, we don't need every algorithm to compute it, right? We just we need at least one algorithm to compute it, right? So we say there exists an algorithm that computes it, right? And what does to compute it mean? Well, it has to give the right answer on input I, right? So now we have to ask, well, which input does it have to give the right answer for? Is it just one input or all inputs, right? It has to give the answer on every input, has to give the right answer. All right. Now, what does this word solves means? Well, it just means the output of the algorithm happens to be the required output for the problem, right? And so now we can say we want to write this sentence in first order logic, right? So we either say for every input there exists an algorithm, or we want to say there exists an algorithm for every input. And that's a place where people struggle with understanding the difference between those. So one thing I really do want you guys to learn is what's the difference between for every input there's an algorithm versus there's an algorithm for every input. All right. Um, so anyway, let's see what order do they appear. And well, the thing is we want one algorithm that works for every input, right? So we have to say there exists one algorithm such that for any input you get the right answer, right? Does that make sense? Um, all right. So one thing I tried when I was teaching to 90, I was trying to teach how people to read these sentences and to understand them. And one thing I recommended is to rip off all the quantifiers and we'll put them on backwards, um, one at a time. And a free variable is a variable that doesn't have any quantifiers, right? So with this bit, a of I equals p of I, it has now we have no quantifier, so everything's a free variable. So we can say what does this statement say, right? And it says algorithm A correctly solves problem P on input I, right? That's what it says. And then we can bring the for all in, right? We want to say, well, which I does it give the right answer for? Well, it gives the right answer for all of I. For all I's, it gives the right answer. And then when we say it in English, what I like to think is forget I because I's not a free variable anymore, right? What is this saying? A sentence says something about its free variables. So now the free variables are A and P. And what does it say about A and P? It says algorithm A correctly computes problem P, right? That's what this says. Why does it compute it? Well, because it gives the right answer on every input, right? Does that make sense? Now we know what this statement sees means, and we can bring in the exists, right? That says there exists some algorithm that solves uh, P, computes P, and now there's only one uh, free variable left, it's P. So what do we want to say about P, right? Well, we can say there exists an algorithm that computes it, but how do we say it without necessarily mentioning A? We say P has the property that it's computable, right? Everybody kind of buy that? Let's not worry about that since it's all right. So, if you've taken the 1090 from George or anyone who teaches it from his book, they do it very formally, and I personally don't feel people get the deep understanding from it. And what I like to teach is how to understand the statement by playing a game. And I really recommend that you learn this game. And I know it might be hard because I I teach an entire term of how to learn this game, so you might not be able to get it from this one thing. But we're going to play this game. All right, so we're going to read the sentence from left to right, and the first thing we read is that there exists an algorithm, and and then what's what's happening is the blue guy is the prover who's trying to prove that this entire sentence is true, right? And what is he trying to prove? He's trying to prove that there exists an algorithm. And you might think, how do you prove that there exists an algorithm? Well, you do it. You prove that something exists by constructing the thing and showing that it's a good thing. All right, so he's the prover is going to produce the algorithm, um, and then and now the prover's goal is to prove that this is true for the algorithm he produces. Now, when we come over to the for all, now how do you prove that something is true for every input? Right? If I want to say it's true for every input, then what you might say in contrast to me, if I say it's true for every input, you might, as my adversary, you might say, I don't know, what about this input? Is it true for that input? And so we're going to have an adversary whose job is to try to prove the sentence is false. And the way he's going to prove it's false is to produce an input that and the reason it matters the order we go is that in this game, the the prover comes up with the algorithm first, and then the adversary, since the adversary goes second, knows the algorithm. So knowing the algorithm, we talk about worst case inputs, and the adversary is going to supply the worst case input. All right, so the adversary tries to give the prover a hard time by producing the input. And then what happens? Now we have all the objects, right? P, what was P? Sorry, I should have mentioned P earlier. P is the free variable, so it's just known by everybody. And we're trying to say about P that P is computable. And we do that by playing this game. Come, all right, so now let's do it again, um, in which we discuss it a little bit more, right? The prover comes up with an algorithm that he claims works. The adversary comes up with an input on which he claims the algorithm doesn't work. And then the prover wins if the algorithm gives the right input. Everybody get that game? And and you might say, yeah, this is exactly what we do in computer science, right? So when you play this game, you get the intuition of what it is we're supposed to be doing. All right. All right. So, and as I said, P is considered free, and so it's not because it's not a bound quantifier, and hence the sentence says something about P. Um, if P is computable, then the prover can come up with an algorithm, right? And come up with an algorithm that no matter what the adversary gives, um, it the algorithm will work. All right. Um, I think that slide got repeated. Sorry about that. I did just put these slides together, never used them before. All right. So um, let's talk about time complexity for a minute. Just to work it in. We want to say not only is P computable, but we might want to say it's computable in n squared time. And so here's the game we're going to add, and we're going to talk about that. So um, we want to say that it's incomputable in n squared time, and now we can play the game. Now you might say here there's an n. N's not talked about anywhere. So what's n? N is the number of bits to represent I. All right, so we're going to represent it this way, right? The N is going to be how much time do you have? You have the number of bits to represent I uh, squared, right? If the input has a billion numbers to sort, then you get a billion squared time to compute sort it, right? That makes sense. And oh, so how does the game work? It's just the same as before. The algorithm, the prover comes up with the machine or an algorithm. The adversary comes up with an input, and then when does the prover win? Well, when the machine gives the right input and gives it in the right time. All right. So before we go on, um, let me tell you what's really frustrated me when teaching 2001, which made me want to teach logic. So this is a picture from the movie Clockwork Orange, which is a horrific movie, but well worth watching. And what I want to train in you is that when you see a sentence like this, you feel physical pain, that this is just your gut says, no, this is a bad statement. And you might notice what's the difference between these. Here, the algorithm, we say exists an algorithm for all inputs, and here we say for all inputs, there exists an algorithm, right? So we want to see what the difference between those are. And so let's talk about a particular problem. Here's the problem is the input is a say a real number x, and the output is we square it, right? And what do we want to say? We want to say that there's a Java program J that gives you the right answer, right? And here's some Java code. Don't don't worry if my Java program isn't always perfect in because it's sort of pseudocode. But here we take an input x and we return the square of the x, right? There's a Java program that can square, and that's what we all know we want. But what is this statement up here saying? It's saying for every input, the game would be adversary gives me input. And then I know the adversary's input. I get to come up with a Java program that works, right? So here for one, if you give me the input one, I just return one. You give me the input two, I return two. You give me three, I return, oh, sorry, not two, four. I return nine, I return 16, right? So here you can see this is saying that for every input, we have a Java program that happens to give the right input, but you know that's not what we mean. And you might think is silly, but we're going to do some hard proofs, and when we're deep down in the proofs, you're going to be confused, and the reason you'll be confused often reason people are confused is the difference between these two statements. We want one algorithm that works for all inputs, right? Versus every input can have its own algorithm, right? All right. So um, we're jumping ahead here. In fact, this won't. this might not be part of the course at all, um, but just to contrast this idea of in this game, the algorithm designer needs to give up the algorithm first, the fixed algorithm, and then the input comes versus the input coming first and then the algorithm comes, right? That sort of subtlety there. Um, let's talk about probabilistic algorithms. You may have learned about um, that if you can flip coins, algorithms do better. And you might say, how possibly can it do better simply by flipping coins? And the reason they do better is is because we change the game that they have to play. All right? So this will give you some idea of different first order logic statements and how the game gets played differently. So just as an example, suppose we have indoors and we promise that half of them have prizes and half of them have goats, or maybe the goat is the prize. Um, and then what does an algorithm do? It says, oh, open this door, then open this door, then open this door. What doors to open? And what does the input specify? It specifies which doors the, have prizes and which doors don't have prizes. Oh, let me tell you something about me, um, is that I'm always, uh, I lose track of what time it is. So, still don't know why I can't see you guys. Maybe if I change the view. Um, So if you note that it's becoming, um, we go from 11:30 to 10 to 1. So if it's 10 to 1, just start making noises and we'll stop. All right? All right. So uh so when we're doing worst case input, the adversary knows the algorithm when it comes up with the input, right? We were saying you spec give me a fixed input, um, and then the adversary comes up with an input, right? And is this fair? Well, it's not really fair because the algorithm says which doors will be opened, and then the algorithm, right? And then the adversary knows which doors will open and will put the prizes behind the doors that aren't open, right? So that's no good. And and so then how many doors do you have to open to just to find one prize? That our goal is to find one prize, and you're going to have to open a half plus one doors in order to find the prize. Does that make sense? And this doesn't seem fair, um, and that's where worst case running time isn't necessarily fair. Everybody see this? That if the algorithm says which doors will be open, then the input gets to choose where to put the prizes, and the adversary will choose the prizes behind the doors that aren't opened. So then, how many doors need to be opened? Well, we promise that half the doors have prizes. So after you've opened up half the doors and gotten uh, non-prizes, then the next door is forced to be a prize. Right? Does that make sense? All right. So, and then here, if we're talking about quicksort, it flips coins um, so that because in quicksort, if you've learned about it, the worst case running time is n squared, but the sort of when you flip coins, the average running time is n log n. So that's kind of what we want to be switching over to. So yeah, so for quicksort, you choose a random pivot, but let's not worry about that because you might not even know what a random pivot is. All right, so now we're going to do the game slightly different. The the algorithm guy, it's going to choose an algorithm that flips coins, And the adversary is going to know the algorithm, the code of this algorithm, but will not know the coin flips. All right. So, so, and what will my algorithm be? My algorithm will be open the doors in a random order, right? I choose the first door to open randomly, and then I choose the next door to open randomly, and the next door to open randomly. And and this means that my algorithm doesn't give any particular order to the doors. One door is no real different than another door. So when the adversary knows the algorithm and doesn't know anything special about the doors, the algorithm, the adversary has no idea which doors to put the prizes behind, right? So he can try to give you the worst case input, but the point is all the inputs are about the same. It doesn't matter which doors you put the prizes behind, right? Does that make sense? All right, and then after the input has been chosen, then we randomly flip the coins, and these coins are flipped sort of independent of what the input was, right? And then when we have the coins flipped, it chooses which doors are open randomly, and so that there's no worst case inputs. All inputs are about the same, but there are worst case coin flips, right? So then what we need is, well, we need the find a prize, right? And then you might have to ask, do we need to find it on every R for most R, right? You can play different games, right? So if half the doors have prizes and you keep flipping coins randomly, then every time you open a door, it's going to have a prize with, if you open up a random door, it will have a prize with probability of half, right? So if you open up T doors randomly, then the probability that you find a no prize is one half raised to the power of T, right? Which um, becomes a small number, right? And so the probability of finding prize is 1 minus this exponential bit. All right, so we can say you choose a random coin flips, and the probability of finding the prize is really high. And then another option, instead of saying um, we run the problem for t time steps, and we have some probability of getting a prize. Another thing is you just keep opening doors until you have a prize. And then by the algorithm, since you keep opening doors, the you're always, for every coin flips, you're going to get a prize. And then you can talk about the expected running time. The expecting running time turns out to be you expect to open up 2 doors, right? Because each door has a probability of half of getting a prize. Any questions about how you guys doing over there? Did you kind of follow this?
Yeah,
You guys
good.
good? Excellent. All right, so here's the problem. Uh, all right, so if P is computable, if there exists an algorithm that works for every input, then we want to think, how do we write down P as uncomputable? And in the logic class, I go through lots of bad things to write here because it's really easy to write this wrong. Um, but the best thing is to just learn how to take negations of things in logic. And there's a mechanical way of doing it, in which is you take you put a negation in front, and as the negation comes in, if it's not true that there exists a machine, then for every machine it's not true. And then if it's not true for every input, then there exists an input in which not true. So then this becomes the statement that P is uncomputable, right? And What is it saying? Well, P is uncomputable. Why? Well, because every machine, every algorithm fails to compute it, right? And why does an algorithm fail to compute problem P? Well, it doesn't have to get the wrong input, the wrong answer on every input. It just has to give the wrong answer on one input, right? Because to compute P, you have to give the right answer on every input. So not if M doesn't compute P, there's some input on which it gives the wrong answer, right? Everybody follow that? Right? So how do you prove this game? If you want to prove that P is uncomputable, then you allow an adversary to give you an arbitrary machine, and then you have to study its machine, even though you don't actually have it. You're just writing down. What you do is write down, let M be arbitrary, and now you have to kind of ask questions about what M is in order to come up with an input, and then prove that the machine gives the wrong answer. And that's really hard to do because there really aren't very many. Um, we don't have very many proofs of things that aren't computable. But one thing we're going to learn in this course, well, you probably know already that sorting is computable. In fact, how do you know something is computable? Well, if you know an algorithm out there to do it, then it's probably computable. And if you don't know an algorithm, like it's probably not computable. So we'll learn about the halting problem, and it's not computable, right? All right, so here's a puzzle to see if you've been listening. Um, Everybody see the sentence? Is this sentence true or not? It says for every input, there's an algorithm, a machine that solves the halting problem. Do you think that, and you know halting problem is undecidable. So what do you think? Do you think this sentence is true or false? I know you're going to be struggling with it, so I won't make you answer. But if you don't know, then you just play the game and see what happens. All right? See the order of quantifiers. Here I've switched the order of quantifiers and it really matters. All right? So let's play the game. The adversary gives me an arbitrary input, right? An input to the halting problem, right? What's the input to the halting problem? Happens to be you give it a Turing machine and an input to that Turing machine, and you want to know yes or no, does that Turing machine halt on the input? But we don't have to worry about that. All I know is I'm given an input to the halting problem, right? And I don't know whether this input that I was giving is a yes or a no input, whether it's an input in which the whole thing answers yes or whether it's an input in which the answer answers no. Why don't I know? I don't know because I don't have an algorithm that solves the whole thing problem, right? So I can't decide which of these is true, but I know that one of them is true, right? So now, what is my goal? Knowing the input, I have to come up with an algorithm. Well, I'm going to come up with two algorithms. My first algorithm called yes, what it does is on every input it says yes. And no, what it does is on every input it says no, right? Now, I don't know which of these algorithms gives the right answer on this input. But I know no matter what the input is, there exists an algorithm that's either this algorithm, one of these two algorithms just happens to give the right answer. I just don't know which. Right? Does that make sense? All right. How's everybody doing? Good?
Good.
I know. Good. All right. So, um, let's keep doing some more logic to get a flavor of how it's useful for us, right? And we're going to find that you might have heard the term sort of runtime error versus compile error. Um, so I first talked about compile phase versus runtime phase, but I switched it to coding phase versus execution phase. But it's kind of what do you do as you're coding versus what happens when you're running the program. All right. And there's, it's useful to know that there's a big split there between these. And so let's see how the split is, right? First, somebody comes along and tells your boss tells you what the computational problem is, right? That's the first thing that happens. And then the exist guy codes up an algorithm. There's our algorithm. And then the adversary guy comes up with an input. And then we run the input to see whether it gets the right answer, right? And we're going to split time between based on what happens before the input versus what happens after the input, right? So what happens before the input, we decide the problem and we come up with an algorithm for it. What happens, and all of these things don't depend on the input, right? So it's the coding phase, it's compile time errors, we don't know the input, right? What happens over here is we actually execute on a particular input, and then this does depend on the input, and you get runtime errors. All right, that makes sense? It's just sometimes I repeat myself. Why do I repeat myself? Is because my feeling is that people didn't get it the first time. All right. So during the construction phase, what do? We come up with the algorithm without knowing the input. And what does the algorithm need? It needs some fixed finite description of the code, right? It could be a description of the Turing machine. It needs to be a description of the Java code. We right? It lays out what all the variables will be, right? And then the input, right, is going to be the input knows the algorithm, and because it knows the algorithm, we can assume that the input is going to be bigger and scarier than the algorithm. Right? The game here is you can come up with a bigger and bigger and fancier and hard to compute and takes more space to write down algorithm. Um, but the adversary knows your algorithm and can come up with a bigger and scarier input uh, than your algorithm, right? So, and as you come up with a bigger input, it might take more time and it might take more dynamically allocated memory, right? So in the coding phase, you have to tell me what my kind of local variables are. I'll have a variable A that's an that's an integer, da 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 da. Oh no, A, here's an algorithm. I'll have a variable X that's an integer and so forth, right? But um, during runtime, you have to allocate malloc uh, more more memory um, as you go along. All right. So let's talk more about these things, right? And when you're writing the algorithm, you have to say how many lines of code you're going to have, right? So we might say, here's a function that says given algorithm A on input I, how many lines of code does it have, right? Now you might say the number of lines of code doesn't depend on the input, and you will say exactly the number of lines doesn't depend on the input, and that's why we're writing it here so that we can say that. All right. We want to express that it doesn't depend. In contrast, the running time does depend on the t. So here, the the running time depends on the input, but the number of lines doesn't. All right. Oh, here's just this is a picture of me, and this is my father who started focusing on runtime more and came up with the idea of polynomial time. All right. So here's a statement that for every algorithm and any input I, the algorithm has to give the right answer, and there'll be some number of lines of code, and there'll be some running time, right? Um, Now, where are we going? Now, here, right now, K and T are free variables, right? We haven't said what K and T are. So, which which K does this? is this going to equal for all k? No, it can this can only equal for some k. There exists a k, right? And similarly, there exists a t, right? It's not all t. It's there exists some t that it has that time. All right. Now, who gets to choose the K and who gets to choose the T? You think about it. Does the programming guy coming up with the code, does he choose the K? Does he choose the T? And what about the adversary? It's coming up with the input. Does the adversary choose the K? Does he choose the T? And the coding phase doesn't depend on the input, and it comes up with a number of lines of code. So here we at coding time we come up with the algorithm that has some number of lines of code, and the 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 running time, however, the running time depends on the input, right? So we come up with the algorithm, a number of lines of code. Then the adversary, knowing this, comes up with an input that might have more running time. So the adversary comes up with the input, and then knowing the input, then there exists some time, right? So, oh, here, does the exist go on this side or on this side? Uh, exist doesn't matter which order you put them in. All right. So here's the sentence. All right. And we can try to think about what it says and how it talks about execution versus coding time. All right. So here's everything's a free variable. So what does it say? Well, it says we get the right answer. We have this number of lines of code. We have this input, right? On input A, I, algorithm A solves problem B with K lines of code and T running time, right? That's what it says. All right, and now we want to, all right, here we're saying solves might be overstating. Why? Because all we're saying is it gives the right answer on this input. We don't know about other inputs, um, right? All right, so now what do we want to say? We want to say I solves the problem. Why? It's not I. Algorithm A solves the problem. What does this say? This says the free variables, uh, right? I guess the free variables um, are no longer I or T, right? So we say A solves problem P with K lines. A has K lines of code and it solves problem P, right? And why does it solve it? Well, because it solves it for every input. It has some running time and gives the right answer, right? Does that make sense? This is saying, right, A solves P. And the time, here the time depends on the input, right? For every input, there is some running time, right? And during coding time, what we're saying is P is computable with some number of lines of code that doesn't depend on the input, right? There's some algorithm that computes it with some number of lines of code, and while the time does depend on the algorithm, right? Um, all right, so then we can play the game. How's the game work? The prover comes up with an algorithm and comes up with an input, right? So that's what he does, right? Oh, this is just going through what the game is again. All right. So um all right, so here to play the game, right? Remember we read it left to right. The prover comes up with the exists, the adversary comes up with the for alls, right? So read it left to right. It says there exists an algorithm, there exists a K. So the prover, knowing, right? P is a free variable, right? So everybody knows P. The prover comes up with the algorithm, comes up with the number of lines of code, and that's happy. And then we come over to for all inputs. What happens in for all inputs? Well, the adversary knows the algorithm and knows the K, and he comes up with some input, right? And then once the input is chosen, the prover has to do their exists, so can come up with what the running time will be, right? Does that make sense? Um, Versus if it's not computable, then the the prover has to come up with an algorithm, but knows there is no algorithm, so just comes up with some input the best as he can, and then the adversary knows that it's not it knows that it's uncomputable, so knows that every algorithm gives the wrong answer on some input. So so given this algorithm that the prover gave, right? That prover gave some algorithm, and the adversary can come up with some input on which it gives the wrong answer. Or maybe it gives the right answer, um, but it takes too long, right? Does that make sense? How am I doing with you guys? Are you okay? Let me look at you again. You guys following okay?
Yeah, it's good.
Everybody good? All right. So now we're going to look at the slides that I made literally an hour ago, and we'll see what you think about them. All right. So what we're going to do first is we're going to, I mean, not today, not in these slides, but in when we start Turing machines, is we're going to define what a Turing machine is and various models of computation, and we're going to talk about how to compile from one model of computation to another model of computation, and for me, um, I guess I've been doing this a long time, so it's just obvious to me how what steps one needs to do in order to prove various things. And it's not as obvious to you guys. And so what I want to be able to do is always write down the first order logic statement of what we're trying to prove, right? Because you're not going to be able to prove it unless you really know what you're trying to prove and you can write it down. And then we'll play the game which we just learned, um, which will show us the steps we have to do in order to prove what we're trying to prove. All right. So let's just first get a sense of what we're going to try to do. We're going to define two models of computation. One is Turing machines and one is Java, and we're going to prove that the two models of computation are equivalent. So Turing is going to define uh, a model of computation. Here it is. There's a Turing machine. We're going to define it probably later today. And um, and then remember Turing's PhD advisor was von Neumann, and von Neumann asked, "What's computable?" And they defined that a problem is computable if there's some Turing machine that computes it. So we want to write that down in logic. We want to say P is a free variable. So we have a sentence here with a free variable that says something about P. We want to say P is computable by a Java program. Why is that? Well, because there exists a Java program that for every input, the Java program will give the required answer. Remember, that's what the first order logic sentence that we were defining before, right? So this here is this red circle is the set of all computational problems P that have Turing machines that solve them, right? However, it turns out we could define computable to be those problems that have Java programs, right? So let's write, and it turns out that the two definitions are equivalent. Why? Because if a boy can do it, a girl can do it better, right? If a Turing machine can do it, then a Java program can simulate it, right? If a Turing machine can do it, a Java program can do it. And conversely, if a Java program can do it, then a Turing machine can do it, right? For any problem, if a Turing machine can do it, if and only if a Java program can do it, right? So here we write down the statement, uh, P is computable by a Turing machine. Why? There is some Turing machine such that for every input, the Turing machine gives you the right answer, right? These are our two statements. And what we want to prove is that statement A is true if and only if Z is true, right? So you have to prove in both directions. If this is true, then this is true. And if this is true, then this is true. But we're only going to prove it in one direction. Why? Because well, we're not even, we're just going to show how to prove it, and that's symmetric. All right. So as the title implies, we prove it by compiling. So here's the compiler. What does the compiler do is you put in to the compiler a Java program, and out of the Java program comes a Turing machine. Out of the compiler comes a Turing machine, right? And this is just, you all have written code in Java, and you've all compiled it into machine code, and then you've run the machine code, unless you have an interpreter that's running it. Let's not worry about that, right? So this is a compiler that will compile it into a Java program, into a Turing machine, right? So what are we saying here? We're saying Java programs can be simulated by Turing machines, right? We're saying any Java program, you give me a Java program, I can give you a Turing machine such that for every input, they give the same answer, right? Right here, you're giving me a Java program. We're playing the game. You give me a Java program. And what will my compiler do? It will produce a Turing machine such that what? Such that they do the same thing. Sorry. And why do they do the same thing? Well, because on every input, uh, they give the same answer, right? Does that make sense? And in all of these, problem P is a free variable that we're making statements about, right? And what do we want to do? Oh, here that this should have come out first. We're trying to prove that if A is true and C is true, then Z is true, right? A and Z gives me, oh, sorry, A and C gives me Z. And you might say, what happened to B? Well, this morning this was much more complicated, and I simplified it down, and we lost B and D, and there might have even been an E. I just brought it down to being as simple as possible. All right. So that's now our goal is to prove that if a problem is solvable by a Java program and you can compile Java programs into Turing machines, then the problem can be solved by a Turing machine, right? And that makes perfect sense, right? Does that make sense? If you can do it, if you can solve P by a Java program and you can convert the Java program into a Turing machine, then there's a Turing machine that can solve the problem. All right? So how do we prove this? Well, if you've taken logic, you know how to prove implies. You assume the left-hand side, all right? So that's here. We're assuming A is true. We're assuming C is true. And when we assume they're true, we're going to have helpers. So here's an oracle, a burning bush that is going to help us assure us that A is true. And we're going to have somebody like in the oracle. Remember that fun oracle? And she's going to assure us that C is true. And having these two helpers, we're going to have to prove that Z is true, right? Does that make sense? And how do we do it? Well, let's first see what our oracles can do for us. What does this oracle do? Well, her job is to assure us that A is true. How does she do it? Well, she already knows computational problem P because it's a free variable. And it says, she says there exists a Java program, right? And so if she's assuring it, how does she assure you that there exists a Java program? Well, she gives you a Java program, right? And then once she's given you a Java program, you're allowed, she then assures you that something's true for every input. And so I can then give her an input, right? And she will assure me that the Java program gives the right answer, right? You understand how that's what this oracle is doing? This oracle saying P is computable by a Java program. Why? Because she can give me a Java program. She says there exists a Java program that computes it. Specifically, it computes it for every input. And if it computes it for every input, then I can give her my favorite input, right? And what will she do? She will prove to me, assure to me that the Java program that she gave me gives the right input on that right answer on that Java on that input, right? People understand this is the game of what A's Oracle is doing for us, right? Versus what C Oracle doing? She's assuring us that Java programs can be simulated by Turing machines, right? She's saying all Java programs, you give me any Java program, right? If it's true for all Java programs, then you can give her an arbitrary Java program. And once you give me the Java program, remember she's a compiler, she's going to compile it into, she's going to prove that there exists the Turing machine. Why? How? By she will construct the Turing machine from the Java program. She knows the Java program. She constructs the Turing machine. And now what is she saying? She's saying that the Java program will be simulated by the Turing machine. What does that mean? Is you give me any arbitrary for all inputs, you give me any arbitrary input, and I can assure you that they do the same thing, right? We don't know what they're going to do, right? You gave me a Java program, I give you a Turing machine, and they're going to do the same thing on the two inputs, right? Does that make sense? So now what do I want to prove? I want to prove the problem P computable by a Turing machine, right? How do I do that? I have to prove Z, right? We all know problem P because it's a free variable. And how do I prove that there exists a Turing machine? Well, I prove there exists a Turing machine by I construct a Turing machine, right? And then, well, now that I've constructed the Turing machine, an adversary is, I have to prove it's true for every input. So the adversary is going to give me an arbitrary input, and I'm going to show that I then have to prove that the Java program, oops, that's not a J, right? That there is an M, right? Let's see if we got it here. This one is M. All right. All right. So everybody get the roles of these three people. And so that they're going to help each other. So what we're going to do is we're going to start with what we want to prove, right? We want to prove that there exists the Turing machine, right? So how do I prove that there exists the Turing machine? Well, I have to construct a Turing machine, right? And how do I construct a Turing machine? I don't know how to construct a Turing machine, right? So I go up to my friends and see which friend can help. This friend here, I give her a Java program, but I don't have a Java program to give her. This this one is going to give me a Java program. All right. She's promising to give me a Java program. I say, great. Give me the Java program, right? So she gives a Java program. Now I have a Java program. What am I going to do with my Java program? Oh, this woman is willing to take a Java program, right? So I give her a Java program. And look at they're both yellow, right? She A gave me a Java program, and I gave A's Java program to C, right? And what does C do with the Java program? She compiles it into a Turing machine, right? Now that gives us the Turing machine that comes from C. And oh, look we need to construct a Turing machine. How convenient. That gives us a Turing machine, right? Does that make sense? How did we come up with a Turing machine? She gave us a Java program. She compiled that Java program into a Turing machine, and now I have a Turing machine. All right. So let's continue on with our game. We constructed a Turing machine, and now the adversary gives me an arbitrary input, right? So here's the input given to me by my adversary, and all of these people, I take the input, uh, A and C, we all take the input given to us by the adversary, right? Now, what is my goal? My goal is to prove this down here, right? How do I prove it? Well, A assures me that the Java program gives the right answer for the computational problem. And C assures me that the Turing machine gives the same answer as the Java program. So I can put them together and get that the Turing machine gives the same answer as the Java program, which gives the same answer as the computational problem, and so we're done. And that is great. Everybody follow that?
Yep.
Excellent. Excellent. Anybody have any questions? I know there are an entire three of you. Dot, I assume Dot is somebody. We used to have a person M, but M didn't want to know the first letter of their name, so now it's M. And Mark, can I give you Mark gold stars because it's really important to have somebody to talk to. You know, I feel like I'm talking to myself, but you're there and you laugh, and I really appreciate it. And what's going to be good for you is I give out class participation marks, and now I'm going to know you and recognize you, and these people will get no class participation marks, even though they came. Why? Because I won't remember this person's name, and I won't remember your name either, Mark, but I'll remember your face.
Oh, come on, Prof. This is the second time.
It's true, but did I remember your name the first time? No,
No.
no, I got a very little brain. All right, so we did logic. Now we're going to come over to models. All right. And we only have 10 minutes left, but we can start this.